Class 13 for college geometry. Today, and on Wednesday as well, we are going to be discussing graphing, or coordinate geometry as they say. Now, anybody here have any of you taken algebra with me, college algebra? Of course, back in the summertime, August, September? Okay. If you did, then most of what we are going to discuss this week is going to be review, because in the algebra course we discussed a bit of graphing as well. Not all of it. Some of it will be new, but most of it will be review. So if you have not taken algebra, that's fine. I'm not going to assume that you know anything, but if you did take algebra already with me a few months ago, then you will hopefully already know a lot of what we're covering this week. Okay, no problem. So you may remember a little bit from then as well. Although the coordinate geometry might have been covered in your geometry class. I mean, the reason why this is also covered in an algebra class is because graphing is a way to illustrate equations in addition to algebraically. You can solve equations. You can also solve equations graphically, so that's why it's part of the algebra course as well. But of course, as you'll see, it's really kind of on the border between algebra and geometry, because we can do a lot of neat geometry things when we're talking about graphing. Okay, first thing we need to do is introduce ourselves to the coordinate plane. The coordinate plane is a way to represent something in two dimensions. That's why this is not just random. This is not just there happens to be an x value and a y value. This is a way you can represent any two things. You can represent poll numbers, for example. If you're representing how well a candidate's doing among two different groups, well, you can represent that on a graph. Any two quantities that you are trying to represent, if you're representing one quantity, quantity A has 50% and quantity B has 40%, well, then you don't need a graph. All you need is a line. You can put one person on the 50 and one person on the 40. It's like in a football game. You can put one person on the 50-yard line, one person on the 40-yard line. But if you want to represent two dimensions, if you want to represent a relationship between two quantities, you can use a coordinate plane. And this is what you have in front of you. On the big screen, you got it a little bigger. On the slide, you got it a little smaller. You have the coordinate plane, and the coordinate plane always has two axes. These axes are these lines that are going back and forth. You've got the x-axis, which is the horizontal axis, and you've got the y-axis, which is the vertex axis. Any point that you put on a coordinate plane, on a graph, has two values. It has an x value and a y value. For example, if I put a point right over here, well, the x value is it starts at 0 in the middle, and it goes positive as you go to the right and negative as you go to the left. The y value starts at 0 in the middle and gets positive as you go upwards and negative as you go downwards. So the point that I put over here, let's see if we can figure out what the coordinates for this point are. And I would count the x value is always notated first. So you have 1, 2, 3, 4. And the y value is the vertical axis. So this would be point 4, 2. Now, can anybody think of an example that has been used basically since the beginning of navigation that uses something very similar to this? Whether you're talking about ship navigation or you're talking about geography in general, the thing that is most similar to this that we hear about in navigation is, of course, longitude and latitude. The entire surface of the globe, every point, has a longitude point and a latitude point. Honestly, I'm not 100% sure what it is in Phoenix. Where I live in New York, the longitude is approximately 75.5 degrees west, and the longitude is approximately 41.5 degrees north. But the point is, with a longitude and latitude point, I can tell you exactly where in the world you are. All you need to say is a longitude point and a latitude point. Now, as it happens to be, because the Earth is 360 degrees, there's 360 degrees in latitude and really 180 degrees. I'm sorry. Well, Anyway, there's 180 degrees in latitude because it goes to the North Pole, which is 90 north, to the South Pole, which is 90 south, and there's 360 degrees in longitude, which goes all the way around the Earth. But if I tell you, 42.687 degrees latitude east and 31.487 degrees latitude latitude north, that is one particular point. There is only one point that meets both criteria. Just like the example on the chart I have over here, on this entire chart there is only one point that meets the 42 criteria. If I put another point, let's say down here, well then it has a positive x value because the x value goes up as it goes to the right, and its positive x value looks like it's 4. The y value on the other because the y value goes down. So this point over here would be the point of 4 and -5. And as you can see that I put over here on the lower right hand side of the slide, there are 4 basic quadrants of the plane. In the upper right hand corner, in other words this quadrant over here, this is quadrant 1. In quadrant 1, all y values are going to be positive and all x values are going to be positive. The x values are positive because it's on the right side of the origin, which is the middle, and the y values are positive because it is in the upper part. In quadrant number 2, which is over here, the quadrants for whatever reason go in counterclockwise. Well, the x values are all going to be negative, and the y values are all going to be positive. Negative x and y. So if I have a point over here, well, the x is negative 1, 2, 3, 4, 5, because it's to the left of the origin, whereas the y value is above the origin, which in this case, the point is -5 and 2. Quadrant 3, which is over here, has a negative x value and a negative y value, because the x is to the left of the origin, 4, and the y is down underneath the origin. So this point is -4, -4. And of course the fourth quadrant, we already named a point over here, is always going to be positive x and negative y. Positive x because it's to the right of the origin, and negative x, negative y here, and it is going to be in the fourth quadrant a negative y value because it is underneath the origin. So again, that's not something that you need to memorize because, let's face it, it's obvious. How far do the x and y axes go? The answer is they go forever. In a correct drawn graph, there should be arrows in all 4 directions on the axes. And the reason for that is the axes theoretically go forever. Now obviously, depending on the size of your graph paper, you're not going to be able to draw them very far. If I told you to graph point 30 and 17, if I did 30 and 17, I wouldn't be able to put it on this paper. 30 on the x-axis would mean 30, which would be well off the screen, and 17 would be higher than the screen. I wouldn't be able to graph it, but it still exists. The point 3017 does exist somewhere, it just is not manifested on this piece of paper itself. That is the coordinate plane, and any two things that I'm trying to tie a relationship to can be plotted on this graph. I don't know if anybody ever reads any statistical analyses or anything like that, but these kinds of graphs are extremely common because these are the ways to plot relationships between 2 points. Let me try to see if I can find a graph. Okay, there we go. This is, anybody ever read this website, 538.com? This is one of my favorite websites of all time. It started off as a political website, and it ended up being, they do all sorts of things now. It's run by Nate Silver, who's kind of a popular statistician. They do some politics and life, science, economics, sports. If you don't read it, by the way, I highly recommend it. It's a very simple website. I'll give you the URL over here just in case anybody happens to be curious. But there it is, 538.com. The 538 is for the number of electoral college votes that are necessary for to win a presidential election. But this is an example, and I just happened to look at a random article on this site because most articles on this site have at least one of these graphs over here. Now, in this example here, they're actually one of them is a quantity, and the other happens to be countries. So this happens to be about a discussion. But in the politics articles, they usually have at least some. They usually have graphs at least one point or another. Okay, there we go. Here's an example. Here is a classic example of a of an x and y value. Now, this is an example of I guess the distinction, the relationship between national polls and how the candidate has actually done. And you can see the x-axis, which is always the horizontal axis, tells you the national average poll 53 to 83 days before the the Iowa caucuses, and then the y-axis, which is the national primary results. And I haven't read this article. I'll probably read it after class at some point because I usually like to read all 538 articles on politics. They're very interesting. But here they're kind of giving you the relationship between how the candidate has done in polling before the primary and during and actually has done in terms of the party itself. So you can see, again, this over here, by the way, this red, anybody know what this red line is called? Which is kind of an amalgamation of all the results, kind of a line that gives you the average of all results. Anybody with a statistics background at all? All right, anyway, this line is called a regression. A regression line is kind of the average of all your data points, kind of the median, the mean of all your data points. So this is an example of a classic chart, a classic coordinate plane, and it's a coordinate plane. It only has one quadrant. Why is this only one quadrant? Our coordinate plane over here had 4 quadrants. Why does this coordinate plane over here only have 1 quadrant? Anybody have any idea? Yeah, does Nate Silver know what he's doing? Is Nate Silver correct to only have one quadrant over here? In fact, most Nate Silver's graphs only have one. Exactly. You can't have negative poll numbers. You can't have negative 6% of people will vote for you. I mean, I suppose there are some candidates that probably deserve negative 6%, but there are no candidates that are actually going to get negative 6%. The lowest possible values you can get in terms of polling numbers are 0. So there's no such thing as a negative value when you're talking about something to that effect. If there are other quantities, if there are charts where it's possible to have a negative quantity, then you'd have to have a full 4-quadrant coordinate plane or a 2-quadrant coordinate plane if it were possible for one quantity to live and not the other. So this is an example. Again, it doesn't have to be, my point is it's not like just a dead thing where it's x and y. It's any 2 quantities that you want to compare can be compared on a coordinate plane. Okay. Let's take a look at, let me get another, hey, one second, where did that one go? Let me get another graph here. Okay, there we go. All right, we'll just settle that right over there for when we need it. Now, you can graph geometric figures as well. The example over here, what shape is that? Okay, this should be an easy one. Okay, it's a triangle, that's right, very good. And there are 3 points over there. You've got B at negative 1, 6, because that's the first, in the second quadrant. Negative 1 x value, 6 y value. Point C is 2, 1, and point A is, of course, negative 2. Again, count 6 over to the negative side and 2 over to the negative side over here. Now, of course, this is a triangle. In order for, other than just to draw it, drawing it in and of itself doesn't mean anything. Just the fact that you can draw a triangle, okay, you know, whoop-de-doo, what does that help you? What does a coordinate plane help you? Well, the way it helps you is that the coordinate plane allows you to be able to make a determination as to the length of these lines and of the slopes of these lines. I'm sorry, not the slopes, but the angles of these lines. A triangle, like a quadrilateral or pretty much any other shape, a lot depends on the lengths of the sides, and a lot depends on the angles. If we know, for example, opposite sides are equal, well then we know, and it's quadrilateral, we know we've got a parallelogram. If opposite sides are equal and we've got a right angle, we've got perpendicular sides, and of course we know that we have a rectangle. If, all the other rules that we've learned about all course, we can apply all of those things to a shape, to a quadrilateral or a line that is plotted on the coordinate plane. And the way you do that is by applying the distance formula. Okay. First of all, I'm going to start you off really, really easy. Okay. Let's say we've got a point over here and a point over here and a line segment that connects them. Let me just draw a normal line segment that connects them. Paint allows me a little bit of a better artist. Okay, there we go. Now, can anybody tell me what the length of that line of that line segment is? Well, how would we figure that out? In terms of boxes, obviously, and the answer, of course, is 6. This point over here is 1, 2, 3. So, 1 second. Okay, so this is 2, 3. And this here is 1, 2, 3, 4, 5, 6, 7, 8, 3. This point is 8, 3. As long as they have the same x value or the same y value, all you have to do is simply count. It's moved boxes over. Now, Tehila brings a good point. This is 6 of whatever units. We don't know what units these are in because we have not actually defined them. We can define them. If you were talking about distances, maybe you'd be talking about miles. If you're talking about election results, maybe you'd be talking about points. Whatever you're talking about, you can always make a determination of what your units are. And the units could be different for x values and y values. In that Nate Silver graph that we saw a little while ago, what were the units of this one? Well, the units of this one were 10 points per box. Each box on the x-axis and each box on the y-axis related to percentage points. Okay, pretty self-explanatory. Now let's look at the more complex case. And the more complex case is when we have lines that are points that are not on the same line. Let's say we've got 1 point over here, and I'm going to leave it in the first quadrant to make things a little simpler. And 1 point over here. Now, 1 second, let's try something else. Okay. All right. Let's say we've got 2 points over here. First of all, let's connect them. And I asked you to figure out what is the distance between these 2 points. Again, in whatever units we happen to be talking about. Okay. To figure out a distance, you have to apply a formula that looks complicated, but in fact is extremely easy. I don't think it's 22. But first of all, let's take it one step at a time before we even apply the formula. Okay, this point down here is 2, and this point up here is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this point up here is 8, and 10. Okay. Now, the distance formula, which is on the slide, is the distance equals the square root of the difference between the x values, x2 minus x1 squared, plus the difference between the y values squared as well. This, as it says in the slide, this entire formula looks very complicated. Okay, no problem. Is it 14? I don't think it's 14 either. But again, let's do it out, and then we'll see what it is. Now, this whole formula over here is really just a derivation of the Pythagorean. Because let's say we were to make a triangle with these two lines. All we'd have to do is take a line here. Let me use a darker color so it's a little more distinguishable. Let's take this line here, and we could draw a line to directly on point. Well, actually, I drew it too far. Sorry. Let me try again. Okay, and let's draw this one down here. If we were to do this, first of all, is this a right triangle? Assuming you have the two purple lines. Yeah, it's a right triangle, because clearly this angle down here is a right angle. So this is a right triangle. So I want to figure out the length of the maroon line, or the length of the dark red line, which of course is now a hypotenuse. What do we need to do? Well, we can use the Pythagorean theorem. The base, the bottom horizontal line is how many boxes long. This one over here is 6, right? Okay. How about this one over here? How long is this? We can take 10 minus 2, or we can just count. Either way, it's 8. So we can use the Pythagorean theorem, a squared plus b squared equals c squared, where c is the hypotenuse. A squared is 6 squared, plus b squared equals, in this case, is 8 squared, equals c squared. So that's 36 plus 64 equals c squared. That's 100 equals c squared. Take the square root of each side, and you've got c equals 10, which is the square root of 100. Of course, it's really plus or minus 10, but we reject the negative value because it's a distance. So this is 10. And this entire formula, if we applied this formula, by the way, we would get the same number. Let's prove that. Distance is the x2 minus x1. So x2 minus x1 is 8 minus 2. So it's 8 minus 2. Whoops, excuse me. 8 minus 2 squared plus y, which is 10 minus 2. So the distance is the square root of 8 minus 2, which is 6 squared, plus 10 minus 2, which is 8 squared. So the distance is the square root of 36, square root of 36 plus 64, which of course is the same thing as the square root of 100, which is 10. The reason for that is because this formula is really the same exact thing as the Pythagorean theorem. Think about it. The Pythagorean theorem is, let me erase this over here so that we get a little bit more room. Alright. The Pythagorean theorem is a squared plus b squared equals c squared. Now, excuse me. When we're trying to figure out the diagonal line, we're always looking for the hypotenuse. If we were looking for a straight line, we wouldn't need this formula. So we're looking for the hypotenuse. And the hypotenuse, what does a represent? What does 6 represent? This represents the difference between the x values. This down here, this point is what over here? This point is 8, 2. So the difference between in the base over here is the difference between the x values, which is the same thing as the second x minus the first x. The next leg, the 8 leg over here, that's the difference between the y values, which is the same thing as y2 minus y1. And of course, it was a squared plus b squared equals c squared, and then isolate c in order to get the square root of this and the square root of that. So overall, you would get this, which is really the exact same formula as the distance formula. If you didn't understand all that, that's okay. The only thing I'm going to ask you to be able to do is either apply this formula, or when you get an actual distance problem, draw your own little right triangle and solve it using the Pythagorean theorem. Which one do you think is easier, by the way? Solving and just drawing the purple lines as I did over here and using the Pythagorean theorem, or using the distance formula? Okay, DeVore says the distance formula. Again, it's a matter of personal choice. There's obviously no right or wrong answer, but either way, you can use whichever formula you like. Okay. Now we've got a couple of other rules, and these are actually much easier than the rules that we've been discussing until now. A point is on the same line as the other 2 points if the sum of the distance between one and the other equals the distance between those points. In other words, if P to Q plus Q to R equals P to R, well then Q has to be on that line. Now, that may seem obvious, and with the line in front of you, it is obvious. But if you weren't sure whether a particular line per point is on the line, that's one way to prove it. To do it in a straight line, I think would illustrate the point. If you have, let's say, a point over here, a point over here, and a point over here. Let's make a line segment that goes across. Okay. Now let's make a straight line segment that goes across. Okay, there we go. If I say this is A, this is B, and this is C, what's the difference between A and B? What's the distance between A and B? Again, we don't have to use the formula or anything like that. We could just count. It's 4, that's right. So AB is 4. What is the distance between B and C? In other words, how long is BC? Also 4. Just count off another 4. 1, 2, 3, 4. How about AC? What's the length of the entire AC? It's 8. Again, simply count them off, or you could just measure the distance in points. Either way, we know that B is on the AC segment because of the fact that AB plus BC equals AC. Certainly 4 plus 4 equals 8. That's one way to prove collinearity, and again, it's an extremely simple concept. Midpoint. The midpoint of a line segment is the average of the x values and the average of the y values. Another very simple, almost obvious point. Let's take 2 points on the same line, then we'll take 2 points on a different line. Let's say I've got these dark red lines over here. I'm sorry, okay, there we go. Okay. This is point A, and this is point B, and I would ask you for the midpoint, in other words, whatever is smack dab in the middle of A and B. Okay, well, let's figure out what each of the points are. Point A is negative 1, 2, 3, 4, 5, 6, 8, 9, and 2 up. So point A is negative 9 and 2. Point B is negative 2 and 2. So, what is the average of the x value? Well, how do you get an average, by the way? An average, you always got to just add the 2 points up and divide by 2. What's negative 9 plus negative 2? Well, negative 9 plus negative 2 is negative 11, because the plus and the minus turn into a minus, so it's negative 9 minus 2, which is negative 11 divided by 2, equals negative 5.5. And how about the y value? What's the average y value? Well, the y value, obviously it's 2, because it didn't change. It was 2 at the beginning. I mean, if you wanted to do the midpoint formula, it would simply be 2 plus 2 divided by 2, which I hope is obvious to everybody that it is 2. So our midpoint is negative 5.5, negative 1, 2, 3, 4, 5.5, and 2. So that is point M, which is negative 5.5 and 2. Let's take one a little bit more complex, but again, nothing too difficult. Let's take this point over here and this point over here. Let's figure out what the midpoint of this line segment is. Let's take a different color so that we don't confuse ourselves. Let's make this point P and this point Q. Well, okay, what is point P? What is the coordinates for point P? Negative 2, right? Because it's in the third quadrant, so it's negative 2, negative 2. How about point Q? Well, let's see. The x value is 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 3, right? Did I count that right? Let me count again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is 9, 3. So, and again, I'm going to cut all this stuff out to give us a little more room here. How do we figure out the midpoint formula? Well, let's add for the x value, we'll add the x's, x1 plus x2 divided by 2. For the y value, we'll add the y's and divide by 2. What are the x values? Well, the x values are negative 2 and 9. And the y value is negative 2 and 3. So the x value is, well, let's see, negative 2 plus 9 is positive 7 over 2. The y value is, I'm sorry, this should be 2. This should be 2, not 3. That should be 1 over 2. Right, exactly. And 7 over 2 is 3.5, and 1 over 2 is 0.5. So our midpoint is 1, 2, 3, and 0.5. So 3.5, yeah. 3.1, 2, 3.5, and 0.5, which is right out over there. Way, I know this goes without saying, but your midpoint had better be on the line. if you write your midpoint's like a point that's off the line, well then obviously that can't possibly be the midpoint. The midpoint has to be on the line By the way, what about down here? What about in this problem? Can anybody figure out what the midpoint is? Well, let's figure it out. In the example that I have have over there, what is point A? Point A looks to be negative 2, positive 4, right? Point B looks to be positive 4, positive 2. So let's figure out the midpoint. Midpoint would be the x values added, negative 2 plus 4 divided by 2, and the y the y values added, 4 plus 2 divided by 2. So that would be 2 over 2 and 6 over 2, so I see 1, 3 as being the midpoint. Okay, right there, and you can see it's right on the line. That's the 1, 3, and you can tell it's the midpoint just by looking at it, but it also is confirmed. Okay, one more concept that I want to discuss before we look at some examples over here, and I've got plenty of good examples. The idea of a slope. A slope is a very important concept when we're talking about lines. We haven't, next time we're going to learn about how to graph lines and how to establish equations that measure relationships between the quantities. Slope is the change in what is happening to a line. Is it going up? Is it going down? Is it going sideways? Is it down? The formula for a slope is the change in y divided by the change in x, whatever that happens to be. So let's an example. We'll take 1 point here, and we'll take 1 point here. Actually, let's get a higher slope. Okay. Let's say we've got a line segment that goes from here to here. And we want to figure out the slope of this line, of this black line over here. Well, again, as usual, the first thing we need to do is establish the points. Now this here is 1, 1, 1, and really we can take any point that's on this, any 2 points on this line. We'll take these 2 points, but if we want wanted to take, for example, this falling straight down is not a slope. There's no, it doesn't move east to west. You're just falling straight down. You'd almost call it an infinite slope. An infinite slope is essentially the same thing as saying an undivided slope. Okay. Two more rules regarding slopes, and then we'll get to a couple of examples. Getting a little late, but hopefully we can get a couple of examples in. Number one, parallel lines have equal slopes. If I draw any two lines with the same slope, I don't know, give me a slope. Who wants to give me a slope? And please don't give me 0.874618731. That wouldn't be very fair, would it? Okay, divorce has 5. I'm going to draw two lines with a slope of 5. So up 5, 1, 2, 3, 4, 5. All right. Okay, that is one line with a slope of 5. Then I'm going to draw another line with a slope of 5. 1, 2, 3, 4, 5. Okay. They both have slopes of 5. They're both 5 up, 1 over, 5 up, 1 over, 5 up, 1 over. What do you notice about them? They're parallel, right? Do you see how they're parallel? Do you see as long as they each run, they're never going to hit each other? The same slope, two lines with the same slope, by definition, are parallel. Perpendicular lines, on the other hand, have slopes that are negative reciprocals. For example, what is reciprocal? Means you flip the fraction. If I had, for example, 4 over 3, the reciprocal would be 3 over 4. Negative reciprocal is the opposite. So what's the negative reciprocal of 5? 5 over 1. What's the negative reciprocal? Negative reciprocal is negative 1/5. So let's draw a line with a slope of negative 1/5. I'll start over here, let's say. And remember, negative means it's going down, and it's going down 1 5 over. It's 1 5 rather than 5 1. So it's down 5 over 1 down, 5 over 1 down, 5 over 1 down. All right. Does this green line look like it's perpendicular to the purple line and the blue line? It better. It has negative reciprocal. And so therefore, this is a right angle with this, and of course, it's a right angle with this also. If it's perpendicular to one parallel line, it's got to be perpendicular to all other lines that are parallel that line as well. Why is this important? Well, because we'll see next time, if we can show, for example, that opposite sides are parallel or perpendicular, well, then we can know what the shape is. You know, for example, if we have, let's take another line down here, and we'll make a 1, 2, 3, 4, 5. Yeah, there we go. Okay. Will this let me fill in? Let's see. No, okay. Okay, alright, it's not going to fill in, but let's say I wanted to fill in this whole, it's good, it's slow. What if I wanted to fill in this whole, you get the point? Alright. See, now I have to fill it in because it's there. You know what Sir George Lee Mallory said when they asked him why he wanted to climb Mount Everest? And he said, because it's there. So I want to fill this in because it's there. Yeah, okay. Alright, what shape is that? The yellow. It's a rectangle, right? How do you know it's a rectangle? Because we've got 4 right angles. The orange and green lines have negative 1/5 slopes, and the purple and blue lines have positive 5 slopes. So therefore, the lines are all parallel to, are all perpendicular with each other, and therefore the yellow shape in the middle is a rectangle. Okay, very good. Now I think we still have a little time for. No, okay, 1 second. Okay, let's bring up Pod as a whiteboard as a. All right. Here I got an interesting one. Okay, we'll save. Put this aside over here. All right, so here's we got an interesting problem. I would do a lot of these, but maybe we'll have time to do a couple of them. But I wanted to do number 9 because I thought that number 9 was very interesting. So let's zoom in a little bit. Let's zoom in, let's say to 150, so you can see a little bit more. Okay, your Aunt Mildred lives in Salt Lake City, Utah, which has approximate coordinates of 41 north, 112 west. Her best friend and pinochle partner, Frederick, lives in Goodwin, Arkansas, with coordinates of 35 north and 91 west, excuse me. They plan to meet halfway between the two cities. Find the coordinates of the halfway point, and for extra credit, give the name of the nearest city to the longitude and latitude that you find. By the way, what kind of graph is this? Which quadrant? Which quadrant are we going to deal over here? Yeah, we only need a 1 quadrant graph over here. But let's first figure out the midpoint. How do you figure out the midpoint? The same way as any other graph. Take the average of the 2 points. Now, if they were in a different quadrant, for example, if instead of 41 north and 35 north, they had, 41 west, 41 north and 35 south, well, then what would you do then? If instead of this being 35 north, this was 35 south, what would you do? Yeah, exactly. Then you can call south negative, or you can call north negative. It really doesn't matter. Either way, you're gonna, it will be fine. But the thing is then you have to draw your graph upside down. And obviously, you'd have north in the bottom and south in the top, which is okay. Nothing inherently wrong with that. There was once a West Wing episode where an organization called Cartographers for Social Justice advocate putting the southern hemisphere on top and the hemisphere on bottom because they thought that because the northern hemisphere is put on tops of globes, people think that Europeans are better than Africans because the north on top. If we flip it around and put Africa on the bottom, on the top, and Europe on the bottom, there wouldn't be as much racism in the world. All right, I'm not going to sit here and discuss the merits of that particular group. I don't know if the group exists or not, but it was an interesting West Wing episode anyway. Anyway, so how would we figure average? The average, let's say, call the north and south, which is the latitude, we'll call that the x-coordinates, and the longitude, actually the latitude, which is north and south, we'll call the y. So the midpoint is x1 plus x2 divided by 2, and y2 plus y1, again, no matter which way. Okay, what's the x? For the x-axis, we'll call the longitude. So that's 112 plus 91, which is, well, yeah, so that's 203 divided by 2, which is 101.5. Good. And on the other side, we've got 41 plus 35 divided by 2, which comes out to 38. So our 101.5 is our 101.5 west longitude, and our 38 is our 38 north latitude. And should we do the extra credit? Give the name of the nearest city to the longitude and latitude that you find. Well, how do we do that? Well, let's go to Google Maps and see if we can do it there. I don't remember. Either you can get out a globe or you can just go to Google Maps. Now, how do you do Google Maps longitude and latitude? I think you can just type it in. So let's try 38 north and 101.5 west. I think you can just do that. Will they let you do that? Yep, there it is. Seems to be empty. .5. 1 second. 1 second. I know that Google Maps lets you do this. Okay, 1 second. How do you format this thing? Yeah. Alright. So this, we didn't have any minutes, so we'll just say okay, let's use the degree signal. What was it? 101.5 west. And what was our north? How many degrees north did we? 38 degrees north. Okay. Huh. Why is my thing not working? 38 degrees north, 101.5 degrees west. Oh, okay. Well, I guess you can just... well, actually, this is not Verizon, but this is in the Phoenix office. But anyway, yeah, that's a good idea. Why not forget maps? Let's just Google it. Okay. Okay, Kendall, Kansas. That's right, as Devorah says. You know, I bet this. Yeah, this thing. Somebody else asked it in Yahoo Answers. I bet some teacher gave this out as a homework. And somebody asked the question on Yahoo Answers to try to figure it out, and somebody told them. So I guess this person did somebody's homework for him or her. Well, okay. Don't do that, everybody. All right. Let's do. We have time for a couple of these. Let's see, since we only have time for a couple of them, let's see if what are the best ones here. Okay, find AB. Who can help me find AB? Well, let's see here. What is point A? It's -3, -4, right? And B is what? B is 4, 3, right? Oops, excuse me. 4, 3. Okay. Now, in order to figure this out, we can use the distance formula, or we can use the Pythagorean theorem. Now, with the Pythagorean theorem, we could draw it, but I don't want to draw this over here. In fact, this is just on a regular web page, so I don't know how to draw it. So I'm going to apply the distance formula. Distance formula was the square root of x2 minus x1 squared plus y2 minus y1 squared as well. Okay. Our second x, let's say b is our second and a is our first, which is fine. So let's say our second x is 4 minus negative 3, because our first x is negative 3. So we'll call that plus 3 squared, plus, and our second y is 3, and, well, minus negative 4, which is plus 4 squared as well. So either way, you've got 7 squared, so d equals 7 squared plus 7 squared, which means d equals the square root of 49 plus 49, which is 98. Good. And how would you break this down? Well, 98 breaks into a perfect square and a non-perfect square. What's the perfect square and the non-perfect square that 98 breaks into? 98 can be broken into the square root of 49 and the square root of 2. And the square root of 49 is, of course, 7, so we can simplify this into 7 times the square root of 2, which should be the answer. Okay. All right. I guess that's pretty much all we have, the time we have for today. And again, there are a lot of these kinds of examples over here, but hopefully this is not too complex. Next time we're going to continue with our discussion of graphing, but we're going to discuss equations. Basically, we're going to discuss how you establish what a line relationship is by virtue of an equation that has an x value and a y value. And we'll apply that to various shapes. We'll apply it to circles even a little bit. We'll figure it out as next time. So, thank you so much, everybody, for coming. I appreciate everybody's attendance and participation.